In our next section, we'll look at the expected value of a probability distribution. Before we get into what that means and represents, I want to talk about a law that connects theoretical probabilities and empirical probabilities. Now, in a small sample size, the empirical probability calculated from an experiment or from data you collect may not exactly match the theoretical probabilities for that situation. For example, if we think about a six-sided die, the theoretical probability of getting a 2 when you roll a die is 1 out of 6 because there's 1 2 out of 6 sides, and each side is equally likely to come up. So 1 out of 6 means we've got a probability of getting a 2 that's about 16.7%. That's theoretically. However, if I were to just roll the die a few times or even 30 times, which I just did, I only got a 2 3 times. So my empirical probability, or the one based on my experiment of rolling the die 30 times, would be 3 out of 10, which is 10%. Now notice 10% does not match up with the theoretical probability. That will often be the case when you have a smaller sample size. However, the larger the sample, the more closely the probability from the experiment will match the theoretical probability. So if I were to roll the die 100 times or 1,000 times or 10,000 times, the more I roll the die, the closer this calculated percent is going to match up with the theoretical percent. This idea actually has a name associated with it. It's called the law of large numbers. In other words, the larger the sample size, the more likely your experimental probability is going to match the theoretical probability. Now, many organizations like insurance companies and casinos rely on this law in order to make a profit because they look at theoretically what the chance is of a player, for instance, hitting a jackpot, and they use that probability to make sure that they charge the right amount to make money. So a casino, again, might pay out big in a jackpot, but they will have calculated using theoretical probabilities how much to charge to play the game, so in the long run, over many, many games played, they come out ahead, even after paying out that big jackpot. So they're going to use the law of large numbers to make sure they make a profit. Expected value. The expected value is the average gain or loss of an event if the experiment is repeated many times. It is calculated by summing the products of the value of each possible event in the experiment and their corresponding probabilities. Here I have that listed out. The expected value is equal to the value of event 1 times its corresponding probability. Notice the little dot between them. Then we add that to the value of event 2 times the corresponding probability of event 2, plus the value of event 3 times the corresponding probability of event 3, plus etc., etc., etc. We keep going until we have looked at each possible event, every possible event in the experiment. A couple of things to be aware of. We have multiplication of the event to the probability, but then we are adding all of those products together. So keep in mind we have both multiplication and addition in this formula. And in order of operations, we need to do the multiplications before we add them up. So we are going to be summing the products of the so we have two calculations here. Using a scientific calculator makes this a really easy calculation though. All right, so when performing this calculation, it can be helpful to organize ourselves ahead of time. Organize all the possible events possible in the experiment and their probabilities into what we call a probability distribution. Probability distributions should always include all possible things that may happen in the experiment. Thus, the probabilities in the table should always add up to 100%, because again, the table includes all possible things that could happen. So 100% of the things that could happen means you have 100% in terms of probability. All right, I have an example of a probability distribution below. I've got two events for this experiment. I have the value of each event listed in the first row, and then the corresponding probability of that event in the second row. To check that this is really a probability distribution, we can add up the probabilities, 5/8 plus 3/8. And when I add them up, I get 8 over 8, which is 1. Now remember, we want our probabilities to add up to 100%. Well, 1 converted to a percent would be 100%. So that's perfect. This is a probability distribution. All right, now let's find the expected value to practice this formula. So the expected value is going to be based on looking at each event in turn and its value and its corresponding probability. So event 1 has a value of $2 and a corresponding probability of 5/8, and I want to multiply those two together. And then add on the same thing for event 2, which would be $12 is the value of the event, and a corresponding probability of 3/8 is multiplied to it. So I take each value multiplied by its corresponding probability, and then I need to add that up. Using a scientific calculator, you can do this pretty easily by entering it all in at once. So I have 2 times 5 divided by 8. So enter a fraction with a division. 2 times 5 divided by 8 plus 12 times 3 divided by 8. If you do that, you should get $5.75. So this is the expected value for this scenario, this experiment. On average, the value in this experiment would be $5.75. Again, this is the average. If you do the experiment many, many, many times, you would get $5.75.